Hi, this is Wendy Galernder from Pace Turf, and today we're going to be tackling the topic of pH. We talk a lot about pH in turf management. The pH of water, the pH of soil, the pH of your spray tank. We talk about the role of pH in suppressing diseases like take-all patch and the role of pH in suppressing weeds such as Poa annua. It's a very complex topic and one that can also get very confusing. And so to clear the air, we are developing a series of short videos on pH. And in this first video, we're going to start by looking at the very basics behind pH, the chemistry behind pH. pH is defined as the negative logarithm of the molar hydrogen ion concentration dissolved in solution. Even though this definition of pH sounds complicated, all it really means is that pH is a measurement of how many hydrogen ions are present in your soil or in your water. To delve into this a little further, I'm going to rely on the use of the term moles. This is an important basic concept in chemistry. If you're not familiar with the concept of moles, take a look at our video, which is titled Avogadro, Moles, and Valence. We have the link to that video accompanying this update. So let's get started with an example of how this equation is used to calculate pH. For this example, we're going to look at a solution that has a hydrogen ion concentration of 0.01 moles and show you how this concentration of hydrogen ions gets translated into a pH of 2. The value of 0.01 can be represented a variety of ways. It's of course equal to the fraction of 1/100th, or 1 over 100. And if you can remember your exponents, you'll realize that this number can also be represented as 10 to the minus 2, as shown here. Exponents are the simplest way to represent numbers with lots of zeros, and it's for this reason that they're used in scientific notation. It's the value of 10 to the minus 2 that you'll need to remember as we look again at the original equation. The original equation asks us what the molar hydrogen ion concentration of our solution is. And we now know that this number is 10 to the minus 2. The log of the number 10 to the minus 2 is minus 2. And if you can't remember about logs, just take my word for it for now. And finally, minus 1 times minus 2 equals the number 2. Thus, our solution with a concentration of 10 to the minus 2 hydrogen ions has a pH of 2. Likewise, if the hydrogen ion concentration is much lower, let's say 0.0001 or 1/10,000th moles, the pH of this solution would be 4. In other words, we see an inverse relationship between the pH value and the concentration of hydrogen ions. The lower the concentration of hydrogen ions, the higher the pH. And the higher the concentration of hydrogen ions, the lower the pH. Just about now, some of you may be saying to yourselves, I thought that pH was a measurement of how acidic a solution is. What do hydrogen ions have to do with that? The answer is that it's the concentration of hydrogen ions that defines whether a solution is either acidic or basic. The more hydrogen ions that are present, the more acidic the solution will be, and the lower the pH will be. And the fewer hydrogen ions that are present, the more basic or alkaline the solution will be, and the higher the pH. If looking at exponents and logs makes your head spin, here's another way to represent hydrogen ion concentration per liter of solution. This will give you an idea of the massive number of hydrogen ions that are present in a liter of solution. That's about a quart. For example, for a pH 14 solution shown at the bottom of this slide, there are 6 billion hydrogen ions per liter. And as pHs get lower, there are even more hydrogen ions present. Now let's take a quick look at the role of pH in soil nutrition. This illustration is a simplified representation of what a soil at pH 7 might look like. The brown, negatively charged soil particle is surrounded by cations such as calcium, magnesium, potassium, and sodium. At pH 7, a neutral pH, which is neither acid or basic, none of the soil cation exchange sites are occupied by hydrogen ions, and the soil is fully loaded with nutrients. This is what we like to see in a soil. But now let's take a look at a soil at pH 5 to understand what changes in an acid soil. In this illustration, you can see that a number of soil cation exchange sites, about 47% of them, are now occupied by hydrogen instead of calcium and magnesium. This is the reason that we avoid low pH conditions in soils. Essential nutrients are displaced at low soil pH. To correct this type of soil, we would use lime, calcium carbonate, or dolomitic lime calcium magnesium carbonate to supply the needed calcium and/or magnesium to increase soil pH and displace the hydrogen ions on the exchange sites. This graph provides a rough estimate of the percentage of the soil exchange sites that will be occupied by hydrogen at various soil pH levels. There are many factors that influence the performance of soils, so this is a simplified model, but it gives you a general idea that at low pHs there are more hydrogen ions on the soil exchange, and as pHs increase, the percentage of hydrogen ions goes down. This introductory video on pH will be followed by others that deal with the role of pH in specific turf management situations. If you need more background information, follow the links that we give you associated with this video, and we'll see you soon. Thanks.